Now, here is our problem. We have critical points, okay? We have candidates for optimality. Suppose that we solved, okay? So let's set our problem. Here is my problem. Problem is I have candidate points x0, candidates for optimality. That is my optimality. Here I am satisfying f prime of x0, which is here the gradient of f at x0. We mix the two notations, okay, equal 0. Okay, so I'm supposing that f is differentiable. Okay, x0 also is an interior point. Okay, belongs to S0 interior. Okay, so now my question is, what is the nature of x0? What is the nature? I mean nature of x0. Is it local max, local mean, or nothing? Neither. Okay, so I need to answer to this question. Okay, so to do that, let's try to see how we can proceed. So in dimension 1, let's go back to dimension 1. We know that we can write approximate f by a linear expression, remember, by its tangent line. In fact, we learned that fx, we approached it by fx0, you remember, plus f prime at x0 times x minus x0. In fact, we can extend, we can have an approximation with higher polynomial, with higher degree of, we can continue. Let's stop at degree 2, and we show, so we have next writing like this one. So it's f second at c, f second an intermediate point c, and over 2 half, so half, and x minus x0 power 2. This is what we call Taylor formula. Okay, so it's not our purpose to enter in details, but we can do that. Okay, we can prove it, and it's feasible. Now suppose that now I have this assumption of the derivative is 0. So if it is 0, then this writing is reduced to fx equal fx0 okay, fx0 plus the half of f second of c of x minus x0 square. But then so finally, to compare fx and fx0, the sign, to deduce a sign of this quantity, it's the same to, it's enough to know the sign of f second at c. Okay, so, and c, of course, here is it's a point, c is between x0 and c, so it's close to x0 some interval. Okay, so if we know a sign of, so if I know that f second c is positive, okay, then so the sign of derivative, if my, in particular, if I have f second at x0 positive, and by continuity, and I use by continuity, and by continuity of a second, I suppose that means more regularity for my higher derivative. F second by continuity, I have f second at c will be then positive. Okay, then I can say that fx minus fx0 is positive or equal 0. That is, okay, that is f second, fx is greater than fx0. Okay, for x belonging to some close interval to x0. Okay, and this is exactly says that is x0 means that x0 is a local minimum, a local mean. Okay, a local mean. So this is the idea, and if you have now f second at x0 is negative, you will get a local maximum. Okay, so let's extend this idea. This idea, yes, we can extend it because we have the following. Okay, so because we can write, let's say for higher, so for higher, we need so for example, we need something like Taylor. Okay, so for n greater than 2, greater than 1, so we can always write, yes, fx, x is here a vector, it will be fx0 plus the gradient of f at x0 dot x minus x0, and we have some term is second evolving second derivative. Let's write it like that, half. So here we are dealing with vectors, so it will be transpose of h. Okay, so here my x, or I can keep it x minus x0. Okay, the Hessian matrix, so it will contain here second derivative of f at an intermediate point, let's call it c. Okay, and plus then and x minus x0, something very similar to what is happening in dimension 1. You see, so if we have this quantity equals 0, we have a critical point, then the sign, the difference will depend on the sign of this quantity. Okay, this time it involves here, so x minus x0, these are vectors, product of, so operation of on matrix and vectors. Okay, it depends on the sign of this quantity and the sign of this quantity. So here I give you what is HF. It's the Hessian. Yes, we know what is the Hessian. So it involves the second derivative. So fx1 x1, fx1 x2, etc. until fx1 xn, and the last one here fxn xn. Okay, so this is our Hessian matrix, fxn x1, and you continue. Okay, so the sign, the comparison will we will need theorems from algebra that ensure us when we have a constant uh, sign of this quantity, knowing information on at x0. Okay, so this is given by the following theorem. So let's, here is the theorem. So let's put it bigger, larger. Okay, so I have to move it. Okay, so here it is, my theorem, my main theorem, and the definition of this determinant that I need to give here. Okay, here it is. Okay, so the theorem, main theorem, it is called a second derivative test. So we have a critical point. We have a function that is regular, C2 function. Okay, and what else we need? So it says that if you take the determinant of the Hessian function matrix at the point, the considered point, you found a critical point. Okay, and you check that the sign is positive for each k from 1 to n. So dk is not the determinant completely, but there's the determinant of, this is d1, then you take a first row up to second column and you cut it, you get d2, etc. So this is how we form our decay. You see, you stop at xk, xk. If you check the sign for each k positive strictly, then is a strict local point, local minimum, because this ensures that you have the positivity of this quantity. Okay, your matrix is definite positive, we call it definite positive. Okay, if so this is, yes, the matrix HF then is definite positive. Okay, HF, for this situation HF is at x x star is definite positive. Okay, so it's the terminology here, it's a definite negative for the second situation. If you have, so the sign is alternating, then you have a strict local maximum. It's strict. Okay, and what else? If now the whole determinant of the Hessian matrix at x star is different from 0, and neither I or 2i are satisfied, then we have a saddle point. So we cannot have a local extreme point. So this is the main theorem, the tool we have to characterize local candidates. Okay, so let's do one example. One example that you, yes, we will see. Yes, this is the function, and let's put it bigger here. Okay, so here is, yes, let's solve the following example. Start from here. Okay, so the example is given. Here is my function fxy. It's, so let's put it bigger here. You can see the values. Okay. Okay, so it's y4. The function is y4 minus 2y2 minus x3 plus 3x. So the question is to find the critical points, and classify them, and classify them if possible. Okay, so here is the question. So let's solve find the answer to that. So we need to solve. Okay, so my function is very indefinitely differentiable, so I can look for the critical points are as solution of the gradient equals 0. So the gradient here, the partial derivative with respect of x, is minus 3x2 plus 3. The partial derivative with respect of y is 4y3 minus 4y. So I need to solve the system 0, 0, so which is equivalent to solve the first equation, 3 times 1 minus x2 equals 0, and so pay attention, you have a system, and 4 times y, so y2 minus 1 equals 0. So then the first equation gives me x equal minus 1 or x equal 1, and we want the second equation to be satisfied, so which is satisfied for y equals 0 or y equal minus 1 or y equal 1. Then from here you have the possible points, x equal minus 1 with y equals 0, x or x equal minus 1 with y equal minus 1, or x equal minus 1 with y equal 1, and or the other 1, x equal 1, y equal 0, or you have x equal 1 and y equal minus 1, or so we have 6 points possible, you see. So be careful, know exactly how to work with this system. So we have 6 points. Okay, so let's apply now. Since I have regularity, I have critical points, so I'm able to test, use the second test derivative. So I need to compute, I will need my Hessian matrix. So the Hessian, okay, so I need fxx, okay, fxy, fxy, which will be the same function, fyy, because my function is regular, Clairaut's theorem. Okay, fxx, so I have fx derived again, minus 6x, fx with respect of y 0, 0, and fy will be 12y2 minus 4. Here is, so my, and now, yes, I can make a test for my example. Okay, Okay, so let's find out. So we can put everything in organize the information on table. Okay. Okay. So you can put your point xy here. You can compute here. So we need to test all the signs d1. So we will have d1 up to n equal to. So we need to d1 at xy. We need d2 then. Okay, d2 at xy. Okay, that's all. Okay, and then conclude about the type. Okay. So let's do it for a few, just one of them, 1 and 0, for example. If I compute 1, 0, so that is, here is d1. So d1 at xy is minus 6x. d2 at xy is the determinant, minus 6x, 0, 0, 12y2 minus, so let's move here, y2 minus 4, okay, which is minus 6x 12y2 minus 4. Okay, so at x equals, so I have minus 6. Okay, and for the determinant I will have minus 6, 0, 0, and minus 4, which is 24. So so we will have here, we satisfy minus 1 d1 positive minus 2 d2 positive, so max point, local max. Okay, for minus 1 1 you will get 6, and for so I'll give you just the values. So positive positive mean, local mean. If you have minus 1 it's 6, and you have 48, so you have another local mean. And here then 1 1, so you have minus 6, compute the values for you. So here, so let's look at this situation. The second, if you multiply by minus 1 d1, you get positive, but minus 1 d2 square is not positive, so we don't, second 2i is not satisfied, and I also is not satisfied because we have negative sign. So dn, now d2 is different from 0. Okay, so it's different from 0, so we have a saddle point. Okay, we have 3 that is satisfied, and the last 2 points also are saddle points. 1 minus 1, you have minus 6 and minus 48, saddle point, so saddle. And the last one is minus 1 0, you have minus 6, plus 6. Okay, and minus 24. Also here we have a saddle point. So we have 3 saddle point, 2 local minimum, and 1 maximum. Okay, local maximum. So we were able to identify the type of each critical point. So if you look at the graph here, so the graph of the surface is here. We don't see very much, but here you see you have here like hyperbola. So here there will be here also hyperbola. So 1, 2, and 3 we have saddle points, and here we have 2 local mean and 1 local max. Okay, so if you read the values, that it will allow you to see the highest value. So here you have minus 291 compared to minus 194, so it's smaller, so that's why we have local minimums. Here you have negative values to that grows to positive values, so it's a local maximum. Okay, so this is how you can read the information. Okay, so this is yes, how we deal with this. So today it was about okay, it was about classification of local extreme points. Okay, so let's write it here. Classification of extreme points. simplification of local extreme point. So here you see how the simple idea that worked for function of one variable has been extended and worked well. Okay, with of course with specific difficulty to the higher dimension. Okay, so we needed tools from algebra that characterize the positivity of a matrix. Okay, the positivity of matrix, which was written here, yes, at the point x star. Okay.